Okay, so welcome to this next video in which we are discussing the function of synaptotagmin, where we're specifically now looking at how it binds to PIP2, phosphatidylinositol 4,5-bisphosphate, which is another constitutive component of the phospholipid bilayer. Okay, so now what I'm going to describe to you is an assay which you can do in order to show that synaptotagmin binds to PIP2. Okay, so what you can do basically is you can have two vesicles like this. So we'll have, let's call them liposomes rather than vesicles. Then we have two liposomes which we have produced, liposome A and liposome B. Okay, so in liposome A we're going to stick synaptotagmin. Okay, so here is our synaptotagmin protein, and we're also actually going to stick synaptobrevin. Now, the reason we put synaptobrevin in is going to be arbitrary. It's not going to be important in this reaction. We're going to use it just at the end, basically, it's there for technical reasons, basically. It's not there because of any sort of biological reason. It's there so that we can actually perform the experiment, and I'll explain why at the end. Okay, so here's, in vesicle A, we have synaptotagmin here and synaptobrevin. Okay, and now what we're going to do is we're going to put PIP2 in the membrane of this liposome B. Okay, so here are PIP2 molecules in the membrane of liposome B. And now, what we want to show is that, in fact, we're going to do slightly more than that. In this experiment, what they do is they also put phosphatidylserine residues in. So this experiment is actually going to do slightly more than show you that synaptotagmin merely binds to PIP2. This is going to show us that this binding to these lipids is enough to promote fusion. If you wanted to show that synaptotagmin binds to PIP2, you could do the same assay as I showed you in the previous video with tryptophan, basically. Well, actually not the tryptophan one, the one prior to that. Okay, so what we're now going to do basically is we're going to actually see whether this is enough to get the fusion of these two vesicles, i.e. whether synaptotagmin here binding to these two lipids, i.e. the C2A domain binding to this phosphatidylserine lipid, and then the C2B domain binding to this PIP2 molecule here, whether that is enough to get fusion of the two liposomes together. Okay, so if it is, then when we mix these liposomes, liposome A with liposome B, they should fuse together. Because the if we put calcium in. So we'll put calcium in as well. Okay, so we take these two types of liposomes, liposome A with synaptotagmin in, and forget the synaptobrevin at the moment, synaptotagmin in, and then liposome B, which has PIP2 in its phospholipid bilayer, and also phosphatidylserine in orange here in its lipid bilayer. Now, if we add calcium, what should happen is the C2A domain, once it's got free calciums bound to it, should bind to the phosphatidylserine, and the C2B domain should bind to phosphatidylinositol 4,5-bisphosphate. And what we want to see is whether the two vesicles actually fuse under this experimental conditions. Okay, so how are we actually going to tell whether they've fused? Well, what we do is we put in a dye, or a fluorophore, or a molecule that will emit light, basically, or will interact with light in some way. We put a dye, basically, into these liposomes. Now, the molecule we're actually going to put in is a dye, but we're going to use it as a fluorophore. Okay, so I will colour this in bright pink. Okay, and this is a molecule known as rhodamine. So we're going to put rhodamine into this vesicle B. So this is rhodamine. Rhodamine. Okay, right. Now, what's going to happen when they fuse together? Well, you're going to get a bigger vesicle here, which now has the rhodamine in, okay? Now, the important thing, this is where synaptobrevin now becomes important. We've got the synaptobrevin in as well. The important thing is that the rhodamine will now be in the same vesicle as the synaptobrevin. Now, what we have is antibodies against synaptobrevin. So, let's show our antibody down here. Remember, antibodies have a heavy chain and a light chain. Like so, 2 heavy chains and 2 light chains bound by disulfide bonds here. So the antibody is basically an anti-synaptobrevin antibody. So this is an anti-synaptobrevin antibody. So this is what we're going to do. So let me just label this up. Synaptobrevin antibody. Synaptobrevin antibody. We will load our anti-synaptobrevin antibody on the walls of some test tube, maybe. Okay? Into that test tube, we'll then add these liposome A's and these liposome B's. Okay? We will then add calcium. Now, calcium, at least in our theory, will bind to the C2A and the C2B domains, and that will cause the C2A and the C2B domains to bind to phosphatidylserine and PIP2, respectively. Okay? If that is enough to cause fusion, then you will get liposomes being produced, bigger liposomes, which have both synaptobrevin and rhodamine in. We then wash out our test tube. Okay? Well, actually, I need to explain something else before then. What's going to happen is the liposomes which have synaptobrevin in are going to attach to the antibody on the wall of the test tube. So, if these two sorts of liposome have fused together, you will have liposomes bound to the wall of the test tube which have rhodamine in, basically, because they'll have rhodamine and synaptobrevin. Synaptobrevin will mean they bind to the wall of the test tube, and the rhodamine is going to mean that they have fluorescent properties which we can look at. Okay? We then wash the test tube out, so that any other vesicles that have not bound to the wall of the test tube are removed. Liposomes that have not bound to the wall of the test tubes are removed. Okay, and then what we do is we look for fluorescent properties on the wall of the test tube. Now, if we find fluorescent properties, that indicates that you have these liposomes which have both synaptobrevin and rhodamine in, and the only way that can have happened is if these two types of liposomes, sorry I'm making this mistake, liposomes are not the same as vesicles. Vesicles are a biological structure which are absolutely full of different proteins in their membranes. Liposomes are these structures that we can make in artificially, which are just balls of lipids in a sort of ball, basically, with a phospholipid bilayer enclosing a little space. They don't have any of the sort of proteins in their membrane that vesicles do. So liposomes and vesicles are not the same thing, and do apologize for that. So if you have liposomes on the wall of the test tube which have rhodamine in, that indicates that you must have had fusion of liposomes A and liposome type B's, okay? Which indicates that this setup was good enough to produce that. If you don't, then it indicates that you haven't had the fusion of liposomes of the type B with liposomes of the type A, which shows us that this setup with synaptotagmin and in one of the vesicles and then PIP2 and PS in the other vesicle is not sufficient to produce liposome fusion. Okay, so when you do this experiment, what you find is that yes, it is sufficient to produce the fusion of the two liposomes, and that's illustrated by the fact that the test tube will have the fluorescent properties of rhodamine. Okay, so this assay really confirms that this works, basically, that synaptotagmin, just binding to PIP2 and PS for its C2b and C2a domains respectively, is good enough to produce fusion of those two liposomes, fusion of two membranes. So this is a good contender, basically, for how synaptotagmin produces exocytosis of those synaptic vesicles in axon terminals.